Time is money. There is probably hardly a business mantra that almost all of us have internalized more than this simple equation. In the next 30 minutes, we will look together at how modern measurement data acquisition helps to save time and even money. Right at the beginning, we will briefly discuss the current general conditions and challenges for measurement technology responsibles. We will take a critical look at the entire measurement data processing procedure, revealing unfavorable scenarios and, of course, also plenty of potential for improvement. Then we will get to know 4 key principles that help us make measurement technology very efficient, and we'll get to know a measurement system that already implements these 4 principles from the core and thus helps us to use time and budget efficiently. And with that, hello and welcome to our latest edition of CSM Explained. My name is Timo Eich. I am Business Development Manager at CSM, and we are going to take a look together at how we can get the most out of your budget and time when it comes to measurement technology. Perhaps you have already had a feeling about this. Time and cost pressures in vehicle development have been increasing in recent months and years. And it's not just only a gut feeling. Many of our customers and partners are telling us so quite frankly. And one of the main reasons for time pressure is the transformation to electromobility and, above all, the politically driven implementation of this. In other words, the fastest possible exit from combustion technology and the switch to electric drive concept. And the various political measures, for example, the tightening of emission limits or the exclusion of entire vehicle classes from urban areas, these create huge time pressure for vehicle manufacturers, but also for end customers. What's more, in the recent years, a whole series of new e-vehicle brands have emerged. For example, in the passenger car sector, all of which naturally want their slice of the pie. And as a result, all vehicle manufacturers, both new and established, are under increasing time pressure to bring new and improved models onto the market. Another important issue is the general shortage of skilled workers, which means, and many of our customers reflect this to us, that more and more work has to be spread across fewer and fewer shoulders, although work is becoming increasingly complex. Now, in the field of measurement technology, we are dealing with a whole range of relatively new components in electromobility for which not that much experience is there. And for some of these components, for example, fuel cells and batteries, new technology knowledge is also required, for example, from the field of chemistry, for which the relevant people in charge have to be trained first. Another problem with new components and systems is most of the simulations for those are still insufficient. Why is that? Because any simulation is only as good as the models on which they rely on. However, for many new applications, there's simply a lack of real data from practice, and models based on purely theoretical considerations often do not withstand reality. This means that driving tests must be carried out already before the simulation starts in order to get valid data for the simulation models. In addition, the complexity of the vehicles has increased significantly, which naturally also leads to a much higher testing effort. And what's more, oftentimes new measurement technology is required for testing new drive concept, for example, analyzers for electrical power, and in general, the need to user safely acquire measured values of various sensor types at high voltage potential. And this means new investments in new technology, measurement technology, hard and software. And recently, we have also experienced direct cost drivers such as the procurement crisis, which has caused a massive rise of cost and delivery times, for example, of electronic components. And finally, personnel and energy costs are rising everywhere, also due to the current inflation. Well, let's summarize the situation. Our resources, namely time and money, continue to decrease even though the complexity of vehicles and their testing continues to increase. So what does that mean? We need to be more efficient with our resources. We need to use the time available to us more efficiently, namely get more work done in the same amount of time. And we need to invest wisely so that our budget is used as efficiently as possible. And specifically in the context of measurement technology and testing, this means that we need measurement technology that is highly efficient. Measurement technology that makes work easier and that is highly available. And measurement technology that is reliable and safe. And we will now develop together what this can look like using the usual measurement data processing procedure. We will briefly go through all the process steps along the way. We will reveal where time and cost traps may be lurking, and of course, identify potential for optimization. So let's start by defining the scope of the investigation. This is where we can already set the course so effectively that we can benefit massively in the further process. Look, if we decide now that not only one specific test will take place in our test vehicle, but that our test vehicle will be used for several tests at the same time, then we can save a lot of time by working in parallel. Of course, we will need more measurement technology for that in our vehicle, and ideally, we use a versatile measurement system that can carry out a wide range of tests simultaneously. Once we have determined the scope of the investigations, we must of course define which measured variables we want to record as part of these investigations, and also determine the measuring points, meaning the locations and components at which measurements are to be taken. And we have to select suitable measuring principles and sensors. And if we want to measure with many different sensors, it is of course very helpful if our measurement system offers the option of reading in a wide variety of sensor types, and that under harsh conditions if needed. Once the measuring points and sensors have been determined, we can then think about the choice of the measurement devices and modules. But what if we are lacking measurement equipment for new applications, let's say electrical power measurement? Then we have to think about it at the latest. Do we now buy a standalone solution, meaning something very special just for this measurement task? Or do we perhaps opt for a versatile, easily expandable overall solution that allows us to react flexibly to new requirements time and time again? Because there's one important point, especially when it comes to time and money, that we must not underestimate, namely the effort involved in installing and configuring the measurement systems. So how easy is it for us to have the hardware properly installed on the test bench, or even more difficult, in the vehicle? Ask someone in your company who's entrusted with the installation of measurement technology in the vehicle on a daily basis, if it's not you yourself, how much time consumption and stress can be avoided with good installation aids. The user friendliness and simplicity of the software are also huge criteria for our customers. So is the software incredibly complex, and do we perhaps need new instructions or training after a 2-month break? Or is the software simple, self-explanatory, and offers configuration aids such as TAT support, signal and sensor databases? A very important point in this consideration. Next step is the calibration of the measuring devices. Many of our customers have to calibrate their measuring devices before every test campaign. And of course, it helps a lot if our measuring devices do not have to be sent to the manufacturer or a calibration service provider every time. But if we can at least partially calibrate them on site. Another point, for example, in electrical power measurement is, do the current transformers have to be laboriously calibrated on the test bench for days? Or can we save a lot of time with an intelligent concept such as the HV breakout module from CSM with integrated current sensors? Because here the calibration is already carried out in the factory and the measurement module is directly ready for immediate use. When carrying out the tests, it of course depends very much on how we have defined the scope of the tests in the first step. But even if we have equipped our test vehicle for several tests, the question is still, do we have to carry out the tests one after another? Or can we actually carry out various tests really at the same time? Because the latter not only saves us time, but also allows us to directly link the test results of several tests, for example, acoustic data and electrical power data. And in this way, we can anticipate some of the offline data analysis and perhaps even react to results already during the tests. Because another very interesting way to increase efficiency is data pre-processing, meaning real-time calculations. Here, our suitable measuring system calculates meaningful parameters from raw data in real time during the data acquisition. For example, we could have our measuring system calculate the active, the reactive, and the apparent power on board from the raw current and voltage signals. And with these calculated parameters, we then have completely new possibilities. For example, we can react directly to these calculated measured variables, or even use them as controller inputs on the test bench, or carry out a massive data reduction through the exclusive transmission of calculated values. Provided we have decided to record several signal sources simultaneously, it is absolutely crucial that the measurement data is precisely synchronized with each other. However, it is often problematic, especially with standalone solutions that work each on their own, if the various data files and time bases then have to be laboriously synchronized manually. In practice, we can really lose a lot of time here. But if our measurement system allows us to write the measurement data from all signal sources synchronized in a single data file with one time base, then of course the data is available for analysis immediately after the measurement. Another way to increase efficiency is by means of intelligent data storage and, in driving tests, remote data transmission. When storing data, triggers, for example, can help us to only record what is relevant to us. Data compression can help to save storage space, and if the data is saved in the correct target format straight away, there are no annoying waiting times for converting file formats afterwards. And in road tests, remote data transmission to a server is a particularly good way of starting offline analysis in parallel while the road test is still running. To do this, of course, we need a data acquisition system that allows smart data storage management and also has a wireless communication tools on board for the road tests. And at some point, the data is transferred and saved, and then it is finally time for offline analysis. And here some exciting questions are raising. Is the data from different signal sources already synchronized in time? And are all the data files in the same file format? Of course, it's extremely helpful if the evaluation can be automated via scripts and if entire test series can be analyzed automatically in one go. And another aspect is the combined analysis of data from different simultaneous tests, such as the aforementioned correlation of acoustic data and power data. And this requires powerful offline analysis tools with open interfaces and modular expandability. And we need still something more for conveniently analyzing entire test series, namely intelligent data storage and smart measurement data management. The questions here is, do we still store data in the traditional way in some file folders, or are we perhaps already using a measurement database with cloud connection and a wide range of analysis options? Here again, we can save huge amounts of time, especially with large test series. Here is the entire measurement data processing procedure at a glance, and we have just talked a lot about the basic optimization potential of the individual process steps. And the question that now arises is, how do we implement this potential in concrete terms? And to answer that questions, I would now like to introduce you to 4 key principles that we believe are crucial for significantly increasing and maximizing the efficiency of measurement data acquisition. And these 4 principles are: number 1, connectivity. By connectivity, we mean the use of powerful bus systems, interfaces, synchronization mechanisms, and file formats for easy connection of distributed measurement technology and its measurement data. And that brings us straight to the second principle. And the second principle is modularity. Modularity allows us to constantly reassemble a flexible measuring system consisting of specialized individual modules in such a way that it is precisely tailored to current requirements. And if we have powerful measurement modules and bus systems at our disposal, then this results in the third principle, and the third principle is scalability. Scalability means that we can implement very small measurement setups and manage huge connected measurement setups with the same modular measurement technology. And if we combine our first 3 principles, it brings us to principle number 4, and that's versatility. By versatility, we simply mean the almost unlimited possibilities of acquiring data from a wide variety of signal sources and performing a wide range of analysis with a single system. And a measurement system that combines these 4 principles: connectivity, modularity, scalability, and versatility, is the Vector CSM e-mobility measurement system. This system consists of a wide variety of modules that can be flexibly combined to meet changing or simultaneous requirements, from analog measurement hardware, bus data, interfaces, and data loggers to measurement data acquisition software and measurement data analysis and data management tools. And we are not going to look at all of these blocks here today, but we will now explore the possible applications of the system using the 4 basic principles just presented and some practical examples. Well, let's start with our first principle, connectivity. For us, connectivity means the use of compatible bus systems, interfaces, synchronization mechanisms, and file formats to connect different software and hardware modules together to form a system. And here's a small example, a power measurement on the electric drivetrain. In fact, we do even more here because we measure the DC power between the battery and the inverter and the mechanical output power on the electric motor via speed and torque, and determine the overall efficiency of the electric drivetrain, plus recording some temperatures on components that operate on high voltage level, such as the inverter or the electric motor. And if we take a look at how the measurement modules are connected with each other, we can see that the various bus systems are in use here, which cover different requirements for the corresponding measurements. We can see devices that are connected via CAN bus here in blue. We can see devices that are connected via Ethercat here in green, and also an XCP on Ethernet connection here in black. Well, let's take a look at these three bus systems. XCP on Ethernet is a high-speed interface that is widely used in the automotive world, especially for in-vehicle applications. And we at CSM use this very fast bus systems primarily because it supports a standardized protocol for synchronizing many distributed bus participants, the so-called PTP, Precision Time Protocol. And this protocol allows us to synchronize fast signal sources with microsecond precision. The second bus systems is Ethercat, also a standard that is widely used in automation, particularly on test benches. At CSM, we use Ethercat as a fast backbone for hundreds of measurement channels and for connecting our modules to test benches. And Ethercat also has a built-in synchronization mechanism, the so-called distributed clock. And for all slower variables, we use the good old CAN bus, which does not offer these high bandwidths, but it's very easy to use and it's incredibly widespread. Now, with these three bus systems, we now are able to set up distributed, very fast and synchronous measurement networks, which is what we mean by the principle of connectivity. And that directly leads us to the second principle, and that's modularity. So we remember modularity means the flexible combination of specialized measurement modules in order to build systems that are precisely tailored to the application. And our goal is to cover a wide range of application and scenarios. For example, modules for test benches and road tests, modules for high voltage applications and modules for low voltage applications, robust modules that are suitable for both test benches and road tests, modules for different speed requirements, meaning different sampling rates, and of course, measuring modules for various measured variables that can occur during the different tests. And at CSM, for example, we offer a very broad and deep portfolio of measurement modules for analog sensors, which covers almost all application scenarios for a wide range of measured variables, for various speed requirements, and for low and high voltage applications. And you may have already noticed that our measurement modules offer a rather small number of measurement channels, and that with a really good reason. This is because we only ever combine exactly the measurement channels that we really need into a system. And we can then use the other measuring channels or modules that we also have at our disposal in other projects at the same time. In this way, our measuring channels are used optimally and efficiently, and this simply saves us money in practice compared to large multi-channel central devices where many measuring channels may be tied up unused in a single test. These have been now the measuring modules for analog sensors, and this portfolio is supplemented by the bus data interfaces of the VN and VX family from Vector Informatic, and our toolbox is completed by powerful fleet loggers and smart loggers from Vector and CSM for data acquisition in road tests. And with this set of different modules, we can now set up distributed measurement networks in almost any combination. Let's move on to our third principle, scalability. And once again, as a reminder, by this we mean the almost unlimited expandability and adaptability of a measuring system thanks to the modular and connected nature of the individual components. So let's take a brief look at this using the example of an electric wheel loader whose four wheels are each driven separately by wheel hub motors. This is what the drive system of this electric wheel loader looks like. We have an HV battery that supplies all the components such as the heater, the cooling system, hydraulic pumps, and of course the four traction motors, each of which is connected to the battery via its own inverter. And if we now want to fully investigate such a drive, we will need measurement data from many points in this drivetrain. And with our connected modular systems, we can now scale our measurement setup to such an extent that we can collect measurement data from many measuring points simultaneously, quickly, and synchronously. This example illustrates the scalability principle of the vector CSM e-mobility measurement systems very well. And that brings us to our fourth principle, and that's versatility. And for us, versatility means that we can solve a wide variety of measurement tasks at the same time and collect and process the measurement data together. Let's take a quick look at the functional test of a fuel cell drive in which a wide range of measured variables must be recorded on both the fuel cell system and the electric drivetrain. This is what the measurement network for this functional test of the fuel cell drive looks like. For example, for your orientation, on the left-hand side in this light gray box is the fuel cell system with the fuel cell stack and the media supply. And on the right-hand side is the drivetrain with the electric motor, inverter, traction battery, and so on. And everywhere on and between all of those components, a wide variety of data is now being collected. For example, physical data such as temperatures, humidity, flow rates, pressures in the media supply and cooling system of the fuel cell stick, which are transmitted via the CAN bus, the line in blue here. Voltage and current values are measured in the high voltage path of the fuel cell system, which are transmitted via EtherCAT because they are simply much faster. And power data is also collected from the drivetrain, which is also transmitted via EtherCAT, the green lines here and here. And in addition, the fast information from the control units of many components is also read out with the help of vector VX interfaces, and these are then transmitted via XCP on Ethernet, the black lines here. And finally, with the help of our data concentrators, all the measurement data ends up in a data acquisition system via XCP on Ethernet, fully synchronized and in a single data file. And as you have probably already noticed, this is not only a great example of the versatility principle, but also of the three other principles of connectivity, modularity, and scalability. A really good example of the performance of the vector CSM e-mobility measurement system. To summarize, we can say that time and budget are increasingly scarce commodity, especially for measurement technology responsibles. By consistently implementing the four key principles, connectivity, modularity, scalability, and versatility, we create the conditions to avoid the stumbling blocks in the measurement data processing procedure and can also leverage valuable optimization treasures. This enables us to use both time and budget as efficiently as possible. And the Vector CSM e-mobility measurement system embodies these four key principles right from its basic idea, making it your loyal companion for implementing your measurement tasks in e-mobility.